Hey Precalculus, I've got a new lesson for you. It's 2.4 number 5. We're talking about graphing rational functions. The name of the game today is vertical asymptotes. And basically I just want you guys to get a feel for, well, not just vertical, but horizontal ones as well. But what do curves look like when they have these dashed lines that break up the graph? And yeah, maybe I'll talk a little bit about domain and range. That's not going to be the primary concern with this, but how about we get started on this example? Yeah. So here's the function we're given. F of x is the same as the y value. So when we look at a function of rational stature, one that can be written as a fraction, there are a couple things that we can piece together on our own. One, when the bottom equals 0, you've got vertical asymptotes. These are places where you can't plug in an x value because you can't divide by 0 there. So the solution to this equation, if you add 3 and divide by 2, again, I just set the denominator, the bottom, equal to 0. I got x equals 3/2 or 1.5, whichever way you want to look at it. That would be my vertical asymptote. I meant to do that. Oh, shadows. Oh my goodness. Where is it? Okay. You know what? Let's just eyeball it. So you got a dashed line that basically splits through your graph at 1.5. So what's about the top? What happens when you set the top equal to 0? Well, these are the places where it crosses the x-axis. It's the zeros of the function. Cross the x-axis at, well, here, whatever this is. At here? Okay, so set 3x plus 6 equal to 0, solve. Minus 6 from both sides. Divide by 3 on both sides. X equals -2. That means -2, 0 is a point that exists for this function. Okay. Now, we've got our vertical asymptotes. We've got our zeros. What about horizontal asymptotes? Well, this is interesting. This is like saying, where does this function live when you go all the way out to basically positive infinity and all the way out to negative infinity? Wait, where are we? Yeah, negative infinity. It's kind of like, what's the leveling off point for this graph? The easiest thing you can do at this point is to plug in a really big number for x. So I'm going to plug in 1,000,000. So it's going to be 3 times 1,000,000, so 3 million plus 6 divided by 2 million minus 3. I got 1.5. Oh, 525. You know, basically, if I do this with a couple more numbers, like if I plug in 1 billion and then 1 trillion, what you're going to find is that the number gets closer and closer. Oop, I graphed it. Didn't mean to do that. Come on now. Closer and closer and closer to 1.5. Too close? All right. Oh, okay. So it's sort of like the powers here are way more dominant than any constant I can add here or there because you're talking about infinite values. So what we do is we draw a horizontal asymptote at 1.5. Are the vertical asymptotes and horizontal asymptotes always going to be the same? No, they are not. All right, so y equals 1.5 is the horizontal asymptote. The shortcut is you take the ratio of the leading powers. I'll talk more about that probably in class, though. That's kind of a hard thing to explain to you guys without feedback. Now, here's what should happen. We now, given our horizontal and vertical asymptotes, plus at least 1 point on the graph, be able to flesh out a curve. You're going to have a curve that goes here, and probably one that goes in the opposite area as well. So now you can just plug in some points. Maybe use that table of function values. Yeah, that's pretty nifty. So, 3x plus 6 divided by 2x minus 3. So my table I'm going to have, let's start at negative 1. Negative 1 corresponds to negative 0.6. 0 corresponds to, I'm sorry, that's positive 1. Negative 1's over here. Negative 1, 0.6. 0, negative 2. 1, negative 9. Oh my, it's down here. What happens when we plug in negative 3? It's only about a third. Negative 4. It's a little bit more than a half. Negative 5. 0.69. Negative 6. 0.8. Negative 7. 0.88. Negative 8. 0.94. At negative 9, it crosses at 1. But it never gets above this horizontal line. Sorry. It's more like this. And then it drops down quick. It's basically bounded by those dotted lines, and they will forever get closer and closer and closer, but never touch them. That's what it means to be an asymptote. The asymptote says, hey, I'm setting a firm boundary here. You can get as close as you want, but don't touch me. That's how the asymptotes work. All right, and then a curve's going to be very similar over here. It's just going to be reflected over this sort of new origin that we've got. Again, you can plug in some points just to figure out what's going on, though. So if I start my table at 2, 2 corresponds to 12, so that's way up there. 3 goes to 1, 2, 3, 4, 5. And we can plot a few more points. 5 goes to 3. 4 is 3.6. And essentially, this is what you got. That's the basics of it. Now let's talk about ones that get a little bit trickier. Like number 2. All right, so the asymptotes. Vertical asymptotes. Set the bottom equal to 0. I can square root both sides. And then subtract 1. So the vertical line x equals negative 1 is a vertical asymptote. How about the horizontals? Well, actually, there's a little rule that you can use here. if the bottom's leading power, which ends up being x squared, all right, if I take x plus 1 times x plus 1, x squared is going to be the one that comes out of that. If the leading power on the bottom is bigger than the leading power up top, which it clearly is, there's not even a variable up top, it's always 0. You want to confirm that? Plug in 1,000,000 in your calculator. You'll find a number that's just a little bit smaller than 0. So the x-axis acts as a boundary. So then we know 2 of these regions are going to be filled with points, 2 curves. It's either going to be here and here, here and here, or in some weird cases, they'll occupy the top 2 spots or the bottom 2 spots. Let's do some investigation with this. It's never going to cross the x-axis, so there are no zeros. No zeros to speak of. So we just got to plot some points. So we go to the table of values, because that's probably the most efficient way to plot points. -1, don't forget that negative out there, divided by x plus 1, inside parentheses, squared. Let's see, what does our table tell us? Plug in a 1, you get -0.25. Plug in 0, you get -1. Plug in -0.5, you get -4. All right, I hope you guys can see what's happening with this pattern here. If I say I go all the way out to 7, the extent to what this graph can go to, I get -0.0156. That's just below the x-axis. So it gets really close to the x-axis right away, but never crosses. On the left-hand side, we're going to table starter at -1. Nope, that's an asymptote. Can't do it. -2. -2 gives me -1. -1.5 gives me -4. Huh, that's interesting. -3 gives me -0.25. Wow, it's like I'm looking at a mirror image. I wonder what -7 is. -7 isn't quite the same number, but that's because it's 6 units from the asymptote. That was 8 units from the asymptote. So it's all symmetry based on with respect to the asymptote. Kind of like with respect to the vertex when you were graphing parabolas. So what can we tell here? The squared here seemed to force everybody in the same direction, when it was just a quantity squared. All right, I'm going to stop this video just to avoid that kind of long video fatigue that I think a lot of us suffer from. So part 2 coming at you very soon.